Log on, tune in, find out. Another good idea from Cambridge.
Amplification.
Well, you won't actually hear the amplification, it's still in there.
Really? So, okay.
It's kind of weird. The sound only goes to the back, so you can't tell.
But there is some output coming out the back, yeah. Good afternoon, everybody. My name is Andy Hopper. I'm the head of the Computer Lab, and I'd like to welcome you all, whether you're from, I guess, some far part of this building I've never seen, from some other part of Cambridge University, and in particular, in addition, if you're from outside the university, you're very, very welcome to the first of our new lecture series, the Distinguished Lecture Series, which we have chosen to call the Wheeler Lectures. There will be one Wheeler lecture a year. At various times in the year, this slot will be changeable according to the schedule of the speakers. And so I hope you nevertheless take note of it, and when it appears, you put it in your diary. And it's a real pleasure. Well, I'm not sure. I think I've seen this lecture theatre this fall before, but it's very rare, or perhaps not quite. In particular, I'd like to thank Steve Clark for organizing this, and Caroline Matthews as well, and for the reception which will take place later. So let me just say a few words about David Wheeler. I'll be just chronological in effect, and then something about our speaker. David Wheeler, as you all no doubt know, is one of the pioneers of computing. He did his undergraduate degree here as a student at Trinity in mathematics, and he graduated in 1948. It is said he did the first PhD in computer science, which he completed in 1951. More importantly, possibly, he married Joyce in 1957, and I'm extremely pleased that, Joyce, you've been able to come and join us on this very special occasion to us, and I hope you enjoy and feel as positive and as happy about it as you possibly can. David became a fellow of Darwin in 1964. He was promoted to professor in 1977. Was elected to the Royal Society in 1981 and, quote, retired in 1994. Of course, he didn't retire, carried on coming here, and it's most definitely in quotes, just stopped getting paid. He was inducted as a fellow of the Computer History Museum in the Valley in 2003, and sadly he died age 77 in 2004, actually here in the department. And you can look it all up, but one of the pioneers of programming, the EDSAX, the first practical computer, the next one, helped build the CAP, helped build the Cambridge Ring, worked on compression, for example, with the Burroughs-Wheeler transform, and on cryptography with the T-block cipher. Fabulous, and so we're very pleased, proud, to have this lecture course, the lecture series named after him. On a purely personal note, he was my PhD supervisor, so I got to know him in that way. I well remember being invited to the Wheeler's house for lunch one Sunday when he became my supervisor, and I also remember trying to understand what he was talking about for the first year, and it took me a good year but the man was absolutely brilliant. But another person supervised by David Wheeler was our speaker today, Bjarne Stroustrup. If you could click on to the next one. And so it is the Golden Jubilee this year, but this photo was taken in the PhD students' room that we shared. And you can see we didn't just have the Queen out of some loyalty, but it was the Diamond Jubilee, 25 years. So this was 1977. And, well, I can't see a difference, actually. Can you see a difference? Mark Pizarro, myself, and a chap called Bruce Croft, who is at the University of Massachusetts and Amherst, and he's god of everything retrieval. So now Bjarne. So he did his maths and CS undergraduate degree at Aarhus, University of Aarhus in 1975. His PhD here in 1979, at which point he went to Bell Labs, AT&T Bell Labs, and he was there until 2002. In 2002, while keeping an affiliation with AT&T Bell Labs, he moved to Texas A&M University, where he's one of the distinguished professors. He was elected to the National Academy of Engineering in 2004, and again, more importantly, he's on sabbatical for the full calendar year here with the office upstairs, so he's come back to the computer lab, and we very much look forward to your talk on C++ 11 style.
I'm very honored to give this first lecture. Very happy that Joyce could come, and I just have to say one or two words about David Wheeler. And I've chosen to pick some quotes that actually says something that we could do well in remembering today. I think sort of everybody could have said the first half of that quote. But the second half, that little caveat that forces you to think a little bit harder, is pure David Wheeler. And I've certainly seen claimed by very credible people that the major problem in systems development these days is too many layers of abstraction. They should have listened. There are attempts to collapse the levels of abstraction to make code easier to understand and faster to run and use less battery power and things like that. And in my opinion, David Wheeler wrote the first article on how to design software. Not just how to string quotes, string instructions together to get code that does what it was supposed to do, but actually how to build libraries and structure software for reuse and composition. And that's 1951. I was in diapers then, and most of you weren't born. And again, if people really could write precise specifications and bury abstractions out of sight, there's another one of these little tales of an idea that adds a sting, correctness and such. Very good. If we could do that, we would be better off. Anyway, so I'll go into the main part of the lecture. Sometimes when the discussion comes about what C++ is, which happens a lot, and especially on the web, I seem to be the only one who doesn't know what it is. Everybody has a firm opinion about what C++ is. They've once written a C++ program, or their professor told them so, so they know the answer. And I have the distinct feeling we're playing blind men and the elephant. If all you've ever done was to pull its tail, you have a pretty good idea of what this beast is like. It's true if all you ever encounter is the tail, but it may not be the right picture of the elephant, and it may not actually be in the best way of using an elephant. So all of these things, well, most of these things are true in some way, but not all. So I've been trying to figure out how to characterize C++, and not being in marketing, I haven't been too successful, but I think C++ is a lightweight abstraction programming language. It's a language where the key to all of the interesting techniques, all the interesting things you can do, is very simple abstractions that are expressive yet cheap in memory consumption, cheap in cycles. And that leads to the key strength of C++, comes when you want to build software infrastructure where your resources are constrained. And at the bottom of every system, there's a lot of constraints that has to be met. So one thing that I find that people tend to forget about software is that not all projects have the same constraints. It's that blind man of the elephant thing again. If you are writing web apps, you may get the idea that JavaScript is all you ever need. If you think slightly deeper, of course, somebody has to implement your JavaScript engine and your browser. But so nobody can say what sort of all software should be. If somebody comes and tells you you have a perfect programming language, it's either a salesman or somebody who hasn't a clue. So we choose our tools based on the resources we need in hardware, software, power, people, whatever comes in. Developer skills is one of the major things here. And so when we're talking about things, we can think about extremes like all that matters is to get to market first. Doesn't matter if the thing's buggy. It'll do until the next release. And then there are other areas where, well, you know, if the program fails, somebody dies. Very different kinds of world, very different kind of concerns, and I hope done by a very different kind of people with a different focus on things. The other thing that I was reminded about first by a guy that was doing this software for Amadeus, for the airline reservation, is, you know, if you double or triple the requirements on hardware from your programming language, you have to buy yourself a new server farm or a new sort of 64 processor machine, and you just blew sort of dollars in the dozens of dollars or hundreds of dollars or millions of dollars category, and that puts another set of constraints on things. I must say I'm more interested in the last two categories there than in the first, and that's probably good because I'm not particularly good at web apps, except if you want them to run native and fast and low battery and such, but that's not the majority. So what I'm looking for is a synthesis of what features do you have, what techniques do you have for using those features, so that we can give better guidance of how to write code. And what I'm working on now, after having worked on getting a new C++ standard, is guidance for its use. That's what I refer to as style. And some of you have heard this idea about C++ being a multi-paradigm language. That's could be true. You can use various programming paradigms for it, but these paradigms were never meant to be used in isolation. And the key effective techniques tend to go beyond the usual styles, whichever is usual to you. I mean, if you write classical C, you miss a point. If everything is a class hierarchy, you miss another point, and so on. So we have to do better than that, and this is what I'm sort of searching for. I'm not quite there, but we're making progress. We want something that's easy to understand for humans and tools. We want things to be modular. We want effective resource management, because the key thing in the areas I'm most interested in is handling resources. A resource, not just memory, but locks, files, sockets, lots of other things. And the world seems to be multi-threaded, multi-concurrent in many different ways, so we need to deal with threads in a safe way, in a type-safe way. We need performance, and how you can get that is part of this talk. and we want portability unless otherwise specified. I'm not interested in perfect portability to all computers in the world, because one of the things I want to do is to exploit the aspects of a particular computer, and as soon as you want to do that, the program will not run in a reasonable way, reasonable performance on a machine that just doesn't have those facilities. So I'm going to give a talk here. It's going through a series of example-based discussions. First I'll tell you a little bit about what I don't like and why, and then go through the other examples. This is not actually a talk about C++ 11, the new ISO standard from last year. It's about how to use it. If you want a feature-for-feature description of C++ 11, I suggest my C++ 11 FAQ. If you can type into Google or another search engine, you can find it. And one thing that's worth remembering, that most of what C++ 11 is already shipping in some compiler or other. There's no compiler that does every bit of C++. There's some discussion when this will happen. Will it happen this year or in the beginning of next year? There seems to be a race between Clang and GCC, and Microsoft is scrambling to get on with it also. But lots of this is shipping. Lots of it can be used today, and they all ship the libraries. So here's a piece of code I don't like. It's qsort, and if you look at the interface of qsort, it's really odd. It sorts memory, but you can't sort memory. You sort values of some type, but it's not there in the interface. You just have the memory to be sorted, the number of elements, number of bytes, and then a comparison function that takes two pieces of memory and compares it. And so if I have to use it, you have there, I want some doubles and some integers sorted, and try and explain that to a novice. I have a comparison string function, a compare double function, and then I say it's passed n doubles. Here's this m of the array. No, it doesn't know how many elements there are in an array. The obvious answer from a naive person is, you mean the machine doesn't know the size of a double? Of course it knows the size of a double, but we've just thrown away the information that it was a double, so we have to tell it again. That's an opportunity for a bug. And comparison functions have to be written in terms of memory. So you have some memory, some value of some type, then you have to throw it away to pass it through this typeless interface. Then you have to give it back again, explicitly. Again, why do I have to do that? It's an opportunity for bugs, and you write this awful kind of code just to compare two doubles, because there's no way in the old style C to say just use the compare operation that's on your machine. So you get this indirect function call, and indirect function calls, indirection in general, are poison to performance and optimization, and you prevent inlining to make sure that you run all of these instructions. Anyway, so I don't like that. It's too big, it's too error prone, and the implementation is really awful. There's inside of a qsort. Now, many of you have seen a qsort, but I did a quick survey to write this. Out of the 20 or so implementations I found on the web, all but 2 were fakes. They were simplified so that you could see how to do it elegantly. In other words, they're taken away this little problem with the arbitrary data types and indirect function calls for comparison, and the example was how to compare a string, or how to compare qsort for a string, qsort for an integer. So the complexity did away. If you look at one of the real ones, you see things like this. Here in particular, it's swapping bytes. If I want to swap 2 values, I mean, if they're doubles, I can swap the word that has the double. You can almost always do better than bytes. Maybe a super clever optimizer can do better, but often you can't apply it because there's so many indirections on the way. And then you call all of these indirect function calls. Again, it's really hard to get efficient. So this is this is the kind of code I don't like. It's untyped, it's full of casts, it's full of clever tricks. We want to do better. And so the obvious question about this is this unfair? Am I picking a straw man? Only partly so, at least. I didn't make up this example. Q-sort is not uncommonly used in education, and they show things like that. Also, it's real code. It's been widely used worldwide for 30 plus years. And the style is not uncommon in production code. And you know, if you think this is bad, you should see what they suggest on the bulletin boards, where the inexperienced teach the novices. And also, the worst thing is that students get this idea that it's cool to write code like that. This is what real programmers do. This is efficient. If it's that complicated, it has to be efficient, right? If it's complicated and low level, it runs fast. No, but I've heard this so often. Whenever I teach freshmen, there's always sort of 10 or 20 people out there that whisper to the others, don't believe what the professor says. This is much cooler. I saw it on the bulletin board. And it's that kind of stuff that is. So I'm not, I think I have a real problem here, not just a straw man. It's probably worse in C and C++, but other languages have different kind of problems. Coming back to JavaScript, you can get some very interesting written code there. And again, so I think bad style is sort of about the #1 problem in real-world C++ code. That should make progress relatively easy, because if it's not the language or the libraries, but the way people use it, then we can teach people to do better. Except in the middle of a million-line program, it's hard to change style. And so bad codes breed more bad codes, so it's hard. And the quickest hack is usually the quickest short-term solution. If you're going to ship tomorrow, you do what you have to do to ship, and then you have to fix the bugs later, and well, the later never comes, and you get bad code forever. And if you look at the textbook, a lot of this is actually taught. So it's important to develop a style that's better and higher level and get it taught. That's one of my concerns. So let's go and look to where we stand. What I would really like in the C++ world is simple, clean interfaces. I wanted to sort anything that could be seen as a container, for instance, a vector and array. I can't quite do that. But if I have a vector, I can sort the vector. That's all there is. I can do this. So we've come a long way from Q-sort, and I'll show you later. This one is not just shorter, more general. It's also significantly faster than Q-sort. Progress happens, even if you sometimes have to wait a decade or two for the solid progress. I want uncompromising performance. I would prefer not to have static type violations. Basically, I can write all the code I'm interested in without getting into type violations. And I don't want any resource leaks. And I don't mean leaked it to a garbage collector that collects the garbage for me. No, I want not to leak, so that we don't have the problem. Okay, so first I'm going to talk a little bit about type-rich programming. Have a look here at some code up here. Increase the speed by a double. What does that mean? Which kind of double? What did the double represent? Or here, draw the object. Can that object be drawn? If an object can be just about anything, as it can in many languages and programming styles, how do you know it has a draw operation? Well, you don't, so you check it at runtime. And here's a rectangle. It takes 4 integers. What do they mean? There's no hint to that. And to show this is right, that's the Mars climate orbiter. It tried to land, except that its altitude was 150 miles different from what it thought. And well, there was a spaceship that didn't make it. And to give a magnitude of this, I read up on it. It was about $560 million. And I'm trying to figure out what does such a big number mean? It means the total salaries of about 200 good engineers for a lifetime. So basically, that was the work of this end of the room, life learnings. It went down. Why did it go down? It went down simply because one group of engineers used the imperial system and the other used the SI units. So somebody had a pressure reported in the wrong units, and it came out the other side 4.65 times what it was supposed to be. So we have to do better in some areas. So here's some little simple. I think we should use types more. If you want to increase speed, it should take a speed. It shouldn't take any old floating point number you could think up. That would take care of it. Draw. If we know it's something we can draw, like it's a shape, that would work. And here's a rectangle. If it takes 2 points, we can draw a thing, or we can take a point and a box and an area. That means that we don't have the problem with adjacent values of the same type. Transpositions is a very common source of errors. And if you can express things more precisely, we can do much better. So I will we'll try and show how that can be done. So here's a solution to the Mars Climate Orbiter problem. And we were all taught it in physics in high school, I believe. I mean, don't do any computations till you've made sure that the units works out. So stick units all around. A speed is something that's meters per second. It is not meters per second squared. It's not a non-unit thing divided by seconds. And you can make the acceleration there. That's a speed divided by some seconds. It'll work out. So why do people not do this? Basically, programming languages don't support that because programming languages are complicated enough as they are, and adding units to the basic structure of a programming language is fairly easy. Any master's students could do it, but they're not the only thing you can add, and this is never added. So to do this, people will have to represent any value as a magnitude unit pair. And if you do that in runtime, you sort of double your amount of memory, and you double the compute time because you have to check the units, doubling approximately. And I can think of two things that are in really short supply on a space probe: memory space and compute time, compute cycles. So people don't do that. They can do this in their heads and get it right. And they do most of the time. I mean, I've certainly done it on paper and on the side and let the program, hope the program was right. But sometimes it goes wrong. So let's see how we could represent this. First, we can have a unit, which I simplify to MKS. A unit is something that says how many meters, kilograms, and seconds it's got. And the value is a unit and a magnitude. Just initialize it with a double, and now it becomes a unit. Speed is a value where the unit is meters per second. Acceleration is a value that has a unit, meters per second squared. That's fairly simple. And we've been able to do that in C++ for at least the last 10 years. And there is at least one good library done at Fermilab that can do all of this, and nobody used it. And I asked the people that designed it and tried to get it into use, why didn't it get used? I mean, it solved the problem I was mentioning before. You can do the units, and it doesn't cost you anything. Well, the answer was notation. This is cryptic, this is weird, we don't want to do it. I mean, these are not computer scientists, they're physicists and engineers, and they're not students, so you can't tell them what to do. So here, people wrote code like that. No way. That is a bit cleaner. They still didn't want to do it. They still wouldn't want to do it. They tried something like that. One, the engineers still didn't want to do it. And two, there's now a good argument that you can't read it. So notation matters immensely. So let's try and fix the notation. And in C++ 11, we can do things like this. We can say there's an operator, this is literal, that's supposed to mean literal. So a literal operator, if you suffix with an S, if you suffix a double with an S, you will return the value with the unit seconds. And here, value with, if you suffix with S2, it's meant to be seconds squared. And now we can write the code like that. This is actually legal running C++ 11, and with the nice properties that it's a compile time only operation, and nothing at runtime. So this is a fairly extreme example of getting the types into the programs, and you can go and catch real bugs. And there's a slight increase in compile time, but for examples this simple, like the whole MKS system, I haven't noticed anybody who could clock them. I mean, obviously there's more work done at compile time, but it's insignificant. Okay, so the rule style rule that comes out of that is keep the interfaces strongly typed and not too general. These interfaces that just takes an int or a double or an object simply ask for trouble. If you have something that is runtime checked, well, then you have to handle exceptions or something. And if it's not runtime checked, well, you get these integers floating around. How do you know it's the right integer? It's a major source of bug. Resources. Here's one of my favorite examples. It's very old. Lots of code is written this way, has been for at least 30 years, because this is pure Unix. So this has been code like this has been around since '74, and this looks like really nice, simple code. We can all read it. Open a file with a name P, and for reading, use F and then close it. This is a significant source of resource leaks, because somehow people manage to get out of this use F without getting to the F close at the end. And of course, if it's been 2 lines, people wouldn't do that, but quite often it's 2 pages. So the first rule of the game is don't write really long functions, but people do. Secondly, if you have a return statement in there, you don't get to the end. If you have a long jump in there, you don't get to the end. And in a language with exceptions, you throw an exception and you don't get to an end. So this leaks. It leaks file handles, possibly also memory. But important thing is file handles. And on an operating system, you usually have a limited, fairly small limit of file systems. And this is a good way of say, hanging your browser. Just leak a few file handles and eventually the system freezes up. So in the terms of exception handling, everybody comes up with this kind of solution. That is, you put a try block around the open, and then you catch any exceptions that happens, clean up your mess, and throw again. You can design a much nicer syntax for this, or at least slightly nicer syntax for this. That's not hard. The problem is that the general logic of what you're doing has become complicated. There's more code here. It's more complex code. And the point is, if I couldn't get this right, why would you expect me to get this right? And remember to write it. I mean, even if this was spelled finally, I could forget to write it. So one of the rules of the game in C++ to write good code is you want to represent your ideas as values of a type. You want to represent things directly in the language. You want to make this a type-rich system. And so what you do, let's see here. One of the problems is that here there's a pointer to something that gets assigned by something, and then it gets closed down. You can read the manual and notice that there's a connection between the open and the close. And if you speak English, it's fairly obvious. But for a lot of resources, it's not that simple. You actually have to go and look at the documentation to figure out what you're doing, and, well, programmers don't. So the problem here is that it's all implicit. It's embedded into some function calls. And so what we should do is represent the notion that we have here, the resource of a file handler, directly, and there it is in sort of you have a couple of constructors for opening the file, and the important thing here is the destructor that closes the file handle. So if we manage to create a file handle, meaning you open the file, then eventually it will be closed, and our code becomes simpler. Give me a file handle to S with the with read access, and that works, and it's widely used in the C++ standard libraries and also not so standard libraries. There's this story that if you give a paleontologist sort of a tiny little bone, he can figure out how the whole dinosaur looked. I'm not sure how true this is, but I have sometimes observed that once you get destructors into the system, you can deduce most of C++ from what it takes to get them to work right. Essentially all except class hierarchies, but it's a very crucial part of C++. So we use RAII, as it's called. Research acquisition is initialization. Sorry about that. We use that for all resources. So here's a modern C++ program, C++11 program. We have a mutex that protects access to some shared memory. This is deliberately oversimplified, but the code is real. I mean, it's just you probably wouldn't protect a single value. Sometimes you do. Anyway, the way you do it is you grab a lock that acquires the mutex. You do your work, and when you leave the scope, the resource is implicitly released. In other words, the lock the mutex is unlocked. So that's all over the place. Now, one thing that you get a lot of in code is resource handles and pointers. So here, somebody's gotten this idea of grabbing a gadget and assigning it to a pointer. This happens a lot. You've seen GUI code, and of course, if you've seen Java and C# code, is all over the place. And so we come down here. We may throw an exception. We may return. In both cases, this gadget has been leaked. And if it's been leaked, well, we can plug in a garbage collector. But what if the gadget owned locks? I mean, it may be a record or something. There's a problem here. So I can remember to delete it and everything's fine, except that if we don't get to the delete, like get out of here with an exception or return, we have leaked. And so we look at this and says, well, let's not have this naked pointer that can be leaked. And people often then put shared pointers in. And shared pointers are just one of these resource handles, like the file handle. It holds the pointer, and when the handle, the pointer, gets out of scope, it releases the resource. That's fine, all works, except I'm not sharing anything with anybody, so why do I want a shared pointer? A shared pointer is sort of the original form of garbage collection. If you read your history, that is exactly what it is. And it has a use count to make sure that the last copy handle to it will release it. But I'm not sharing anything with anybody. So we also have unique pointers, which simply holds an object, doesn't have a use count, but it has a destructor so that if you get out of there, you release the resource. And in both cases, you don't have any delete statement you could forget. News don't belong in general code. Deletes don't belong in general code. If you see the code littered with news and deletes, you can be pretty sure that there's resource leaks. Because if humans have to keep track of a few thousand news and deletes, they're going to get them wrong. So they belong inside places like constructors for handles, and inside abstractions that manage it, like a vector manages its objects on the free store, and things like that. That's where they belong. And anyway, you know, why did I use the free store there? Why did I say new? There's no need to it. It's much better to take a scoped object and everything just works. The destructor for gadget, if there is one, will be fired at the right times. So the simpler code, well, it runs faster and it's more correct. So for resource management, the style guideline I'm trying to come up with is prefer classes where the resource management is part of their fundamental semantics. It should not be some external thing that keeps track of where the resources are, because the external code, the user code, does not know really what the constraints are, what the resources are, because, well, the code is written and the guy looked in the manual and the definition of a gadget may have changed since he looked and things like that. So we would prefer not to have external memory management. We want it local and appropriate to the semantics. Vectors, O-streams, threads behave like that in C++. If you absolutely have to have pointers, like you have to have two places point to an object, use unique pointers or shared pointers to deal with this. At least you don't have to deal with naked pointers. Still, pointers are pointers. If this piece of code has a pointer and this piece of code has a pointer, a shared pointer will take care of the problem of who deletes it. It will not take care of the problem of who writes first and what can you rely on the other part of the code dealing with it. So more localized objects are better. Anyway, if we start getting somewhat radical about not using too many pointers, we have a problem. And in general, how do we get a lot of data out of a function? I mean, the standard solution to that is you pass a pointer around, not large amounts of memory. But logically, that's not such a good thing. Functional programming in all forms is one of the roots of that is that you don't want to have lots of pointers and aliases moving around. You just want to pretend that there's objects. Okay, so let's see. Here's a classical solution. It's a big mistake. You want a matrix that adds two, a matrix add that adds two matrices and returns, well, let's see what it returns. Matrices come in by reference, so we don't have to copy them on the way in, but how do we get it out? Inside the add, you have to make a new object and have to get it out. You might try a pointer, but then your code will look like this. This is simply unacceptable. We have lost our high-level notation. Oh yeah, and who does the delete? I mean, once we've got a pointer coming out, then somebody has to delete. So we can try this, have a reference. Now it looks pretty, but this is even worse. Who does the delete? The obvious question is delete of what? I don't see any pointers. Oh, well, the pointer that's really hidden as a reference. That's not good. No good answer. You have to look further. So we can try and solve it by dropping to sort of assembly code. Just pass in a target which you can fill. And now we have to do this. And basically that is assembly code. Just happens to be assembly code for matrices. It's ugly and well, it is proven unmanageable in a lot of cases. Sometimes it works, but it's not a good strategy. So finally we come to the idea, the obvious thing is that operator plus really is something that given two matrices makes a new matrix. So it has to look like that. That's the logically right thing to do. And we can write this is fine. But how do we do it? If this is a 10,000 by 10,000 matrix, the copy might be noticeable. We would like to, it's too expensive. Then we try and optimize it. There's various brittle hacks like using a stack of matrices or a circular buffer of matrices. They're all brittle. But finally, we don't actually want to copy any matrix. I mean, after all, what do? We make a matrix then we copy it out and we throw the old one away. That's not how we work in the real world. I mean, look at this. Here, I've got an object here. I want it over there. I move it. That's all there is to it. About 6-month-old babies can figure out that the object moved over there again. This is really fundamental. It's just, in computers, we've been so used to the only thing they can do well is copying, that we think in terms of copying. What we want this is, we want it to be a move. And wait a minute, what is a matrix really? A matrix is some kind of handle to a lot of elements. So we're back to this model that we saw with vector and with locks and the file handles. It's a handle pointed down to a resource that's being managed. It's one of these Wheeler indirections. Anyway, so here we want to make a matrix. We want to make R1 to the right thing, and then we want to get it out again by this little trick. We have R in here. It points to the element. We want to take that pointer there and move it into res, cut the connection to R so it points to nothing, and then get out. We've gotten, that way we have gotten the 10,000 by 10,000 elements out by copying one pointer. The way we do that in C++ is we provide a move constructor. So we have copy constructors that copy, and move constructors move, and the general form of move constructor is grab the representation and zero out the original representation so that it's cheap and safe to delete it. And that stuff is all over the standard library of the C++11. Vector, list, forward list, map, unordered map, set, strings, all of those use move constructors. So if you code today, and you, in C++ 98, and you recompile it with C++11, it may actually start speeding up. Especially inside some of the general algorithms, the sorts that moves things around and such, you can get some interesting speed ups simply from this. String manipulation tends to be somewhat faster than it used to be without any change of the source code. That's the interesting thing. We've just turned the moves into, the copies into moves. That works really nicely. So basically, I draw the conclusion, if you see naked pointers in interfaces, in the middle of complicated code, you've probably done something wrong. Keep pointers inside functions and classes. When you have them in a place where an exception can happen, use a unique pointer or a shared pointer to protect it, but naked pointers are somewhat dangerous. We've known that for a long time, we just didn't know what to do about it. And so when I look at a piece of code trying to figure out if it's good or bad, one thing I look for is news and deletes in a lot of places in an unstructured manner, and the move constructors, the return by value but optimize it with a move is an important paradigm. So going sort of, I'm not sure, up or down or sideways, but another concern that we always have in larger programs is how do we represent things? What data structures do we use? And here's an example that John Bentley marched into my office and presented to me about 15 years ago, and asked me a question. So basically the exercise is you want to create a sequence of n random integers. So if you pick them, you put them in an order, and so the sequence grows. It's always an ordered sequence. And once you're finished, you pick a set of positions and you take them out all again afterwards. And so the question is, for what n is it better to use a linked list than a vector to represent that sequence? And I scratched my head, and like most other people, I came up with the wrong answer. There's the performance data that I ran 2 weeks ago, and it's fairly typical. The red line there is the cost of doing the time needed to do a list. And I know we've all been taught in data structures that lists are really good when you insert and remove elements. So most of us guesses that the vectors might be good for really short things, but really for real code you have to use lists. This is just wrong. I've had a student who worked 48 hours, I think, trying to find the bug in his program because he got these curves. There's no bug. By the way, some people say, well, yeah, vectors are better than lists because the allocation of all of these elements for lists are expensive, so I just optimize it. That is pre-allocated space for the lists, whereas this one is just using the out-of-the-box automatic handling of memory. So that's not it. What actually happens is that there's a linear search to get the insertion point and to get to the deletion point. Of course, with vectors, you can go straight to the deletion point because it's a position, and you could use a binary search to find the insertion point. You could optimize this. But to be fair, I didn't do those optimizations for vector. I used the inefficient one just like a list. And it really is inefficient. The whole thing, if you do complexity theory, or if you just think about it, or if you measure it, it's the linear search for the insertion and deletion point that dominates everything. And basically, the first problem is that vectors are an inefficient representation of small data, because you need the previous pointer, the next pointer, and you need them to be over on some free store, and you get some extra memory there. You can optimize that by a pool allocator, which was I did for the green line, but still, you know, by saying list for integers, I quadrupled the amount of memory I'm using. Furthermore, modern machines really like to do things that fits well with caches, and moving a series of adjacent integers, as you have to do, you put something into a vector, and you have to move all the elements one over, or if you take one out, you have to move them back again. Lists don't have that problem. But, you know, if you want to move 10,000 integers over one position, modern hardware is really, really good at that. On the other hand, what happens when you want to find a list? They are now ordered, which means they are sort of completely scrambled in their position in memory. So even if you are completely in the cache, the access pattern looks sort of like that. Whereas for lists, for vectors, it's just like that. And the results are spectacular. So modern architectures, even with lots of memory, it's nice to have compact data. And when you talk to people that has resource constraints, sort of the Googles and the cell phone providers of the world, compact data and systematic access to the data, predictable access to the data is really important. Some people have sort of looked at this and says, I don't have linked lists of 100,000 elements or vectors of 100,000 elements, but you can get exactly the same effects by individual elements. Here is a vector of points initialized to 4 points like that, and you get a data structure like this, basically a contiguous representation in memory of the elements. If you go to a true object-oriented style, which is your only choice in some languages unless you start playing games, you get a reference to the vector data structure, which contains a vector of 4 references to the elements. And so the amount of memory used here is about twice as much, but more importantly, it's scattered in memory, and to get to any coordinate, you get 1, 2, 3 indirections. Here, you get 1. The difference is quite spectacular. So you can get these effects simply from an individual object. And of course, if you have lots of individual objects, this effect duplicates just like having sort of a linked list versus vector. Okay, so if we simplify our data structures, we we get performance. It's also easier to think about. But I think to get reliability and performance, we actually have to think about how we write code. We have to get our code more regular, more understandable. And here's a sort of a case study that I ran into actually last year. Some friends probably shouldn't say where they work. But anyway, this is real code. So the problem was you have a GUI, and very often we sort of drag something over and stick it in another place. Think about rearranging your taskbar on a browser. Pick this one up and stick it in the middle. So you have an insertion point. You have to move some over to make room. And the code for doing that was fairly messy. 25 lines of code. This is a small example, so I can talk about it. There was 1 loop, 3 tests, and 14 function calls to do what I just said. And the guy who wrote this code sort of looked at it, scratched his head, says, "Is this correct? I mean, how do I know? There's still this much code, and it was fairly complicated. It's maintainable. I mean, if you have to scratch your head and think about that after having written and debugged it, it's probably not maintainable. I mean, you should be certain. And is it usable elsewhere? No, it's completely special purpose code. It's code for moving particular objects into particular data structures for a particular GUI. So this is where professionalism came in. He went and asked some friends to get a review of this code to see if they could approve it. There still are professionalism in this field. This is good. So anyway, the next thing was they analyzed it for a while and realized that what are we doing? You have to do a find if to find the insertion point. Just test the elements till you find the one that matches the predicate. And so you do this, find the first that contains P, which was what happens to be the name of the predicate, finding the insertion point, and then you can rotate it in. This is much shorter. There's no explicit loops. The rotate function, the find if, are standard library functions, and actually among the ones that people use fairly often, so you'd expect an expert C++ programmer to actually understand this. And this is fine. I would consider this comprehensible and maintainable. Still special purpose. This vector here was a vector of objects and this. And what's a coordinate and contains? Very, very special purpose. So after another thought, they generalized it in this function called gather, which is shipped by actually a couple of toolkits now. It says make a pair of, you partition it, everything before the insertion point, everything after the insertion point, and that's done. This, by the way, since it's a predicate, works for more than one element. So you can take, as you sometimes do, pick this, and this, and stick it in one place, and that's the code that does it. These are admittedly not among the standard library functions that everybody can remember what they do, but you can look it up. They are well specified. Standard functions tend to be much better specified than things that have been written once and used once by a single programmer. So no loops, no tests. We can actually get the code fairly clean. And so basically, I think we have to focus on algorithms and consider generality of use, and that is this is going to be very difficult because there's a hacker culture, especially among the systems programmers, and the effect that made people think that low level must be efficient has an effect here. People are not used to think in terms of algorithms, at least not as much as they should, but consider large functions suspect. If you have a lot of code like this, why? I mean, there are code that's much longer than this that is there because people were afraid of function calls. None of the function calls in the last time I encountered this was in a tight loop. I mean, the code could easily be chopped into 10, 15 smaller functions. And if you do that, you can name the things. If you can't name your function, you probably don't know what it's doing. Furthermore, you don't get interference with variables from different parts in a large function. So small functions are by and large good, and in most cases you can afford it. This is very basic kind of stuff. It just doesn't happen in real life as much as it should do. And I consider every complicated control structure suspect, and I would much rather they were embedded in well-named, well-tested algorithms. And so basically, when you can, stay high level. By the way, this is a picture of Mauna Loa taken from the peak of Mauna Kea on Hawaii. And if I sometimes waffle a bit, it may be because I just spent 40 hours flying back from Hawaii and I'm seriously jet lagged. This is not a picture from 2 days ago, but it could have been. So anyway, back to this equation in many people's mind between low level and efficient. Low level is not necessarily efficient. Sometimes you have to write low level code, and certainly I do not think for the kind of applications I am thinking about that we can ignore efficiency. It's just writing ugly code is not the main way to get efficiency. So here is a little example. Here's a perfectly ordinary for loop. And there's even people who write this with pointers so that they don't have to write VF subscript. But that doesn't matter for performance. Hasn't mattered for performance in C and C++ since the early 80s. But people still haven't noticed. But anyway, take this one. Take this modern thing here, which is for each for a sequence and using the lambda that sums things up. I timed this with a number of compilers on a number of systems, and I couldn't tell the difference. It's equally efficient. This is a very trivial algorithm, and this is a very trivial loop. But if the algorithm was something more complicated, like a breadth-first search, this code would still look the same, except that it would say breadth first there. Here, we would have to write some very complicated code. So going towards a more algorithmic style, we can only do if we can afford to, and this example and similar example says that we can. The compilers and optimizers are now such that we can afford to write code, explicit algorithm or a sequence, generalized sequence, and passing in a lambda. We can afford it. Again, coming back to sort versus Q-sort, the difference is about 2.5 times in favor of the C++ version. The main reason, type safety, inlining, better anti-alias-based optimization, it just works better. If you are using C styles and OO style, you don't get any difference in performance, but you can actually do better by moving to a more style. I think sort is typical in its performance implications relative to the amount of abstraction you can provide. In other words, I can increase the abstraction level and at the same time improve performance, and the reason here, more optimization can be done. And so don't lower the level of abstraction without reason. People do it without a reason. They optimize just because they think the messier code must be more efficient. Don't do that. Measure. And low level gives more code, more bugs, and higher maintenance cost. And that's not good. I'm not going to say much about inheritance. There's so much of it these days that there's no point in me explaining it because you know it already. I'll just point out that it's really good to have an inheritance hierarchy, a hierarchical ordering, provided the domain concept is genuinely hierarchical. It should come from the application, from the concepts we're dealing with, not just because you like the look of virtual function calls better than the look of an ordinary function call. So inheritance have been, I think, seriously and systematically overused and misused, and still is being so. Anyway, let me say something about concurrency. Since essentially all hardware these days is concurrent, we better deal with it. Everything I said would be quite irrelevant if you couldn't stay high level, if you couldn't stay abstract, if you couldn't stay type safe when you had to use a concurrency mechanism. So we have to get type safe concurrency, and we can do that. Here's an example, trivially simple example, but it shows the general idea. I have a function I would like to execute, and I have a function object I would like to execute. And here is it. We make a thread that says that f should be called for vector of 1. And we have a thread that says t2, f of vector 2 should be executed, each in a separate thread. So we spawn those two threads, we join them, and now we can use the results. This is classical, boring thread code. And in my opinion, threads and locks is the worst way of writing concurrent programs, but it's the common one, it's the one most people use. We have to be able to do it well. If you've written POSIX stuff or threading in C, you'll know something here. There's no void stars, there's no casts. Everything is just sort of the same type system, the same kind of abstractions as we do for single-threaded code. And the problems are still the same in concurrency. You better not have race conditions and all the rest of the stuff, but we can do that type safe. So we're just taking the system level concurrency that a systems programming language like C++ has to do well, and introducing type safety. And here's a slightly higher model. Is it? This was not what I meant to write. Okay, this is just the same thing. Let's go to the next, because it's here's a better example of how you can do concurrent stuff. We have two functions, f and g. They both do something to a vector, const vector, so they only read it. And I can say I would like to spawn something that does f for some vec, and I want to spawn something that can do g for some vec. Back I get actually handles to the tasks. These are futures. If you can think about these are tasks like spawns in a system with threads, with work stealing. And so I can get the first result, I can get the second result, and use them. Some number of threads may be spawned here. We don't know how many, but we just wait when we get to the end. So we can do slightly better than the basic level of abstraction for concurrency. With threads, we can go to some task-based concurrencies, and I hope to see many more libraries based on ideas that are higher level like this, because we provide the foundation for it. And so, to sum up, I'm encouraging people to do more type-rich programming. People have been talking about it for a long time, but we should do more about it. The interfaces can be improved. We need to use a lot of simple classes. They are dirt cheap, meaning they cost nothing in many cases. Think of those value types with units. Many classes are really cheap. Even a matrix class is cheap to move around if you're using moves. And avoid or general interfaces. That is, the interfaces has to be specified in terms of types that are expressive, not just the integers and the objects. And the resource management and error handling should be integrated. The default way of doing this is this resource acquisition is initialization technique, and prefer move to complicated pointer use You can't optimize when you've got pointers, and you tend to get bugs if you have too many of them. And use compact data structures. That tends to be the key to performance. Try to move towards a heavier use of more formally specified algorithms. And the way to do of all of that is to build libraries that does it. Because when we're in a hurry to deliver an application, we probably can't think this through to the extent that a library provider, library designer can. And then I'll just take questions.
So off we go. Let's go and have some questions. Sir.
Looking at your vector example of insertion and deletion,
Yeah.
the traditional view there would mean that this would be expensive if you've got classes which are difficult to copy. Presumably now you've got the new semantics in there, the moving from items up in a vector suddenly become a lot more efficient, and that takes a look away at the creator.
Let's see, the comment was that move semantics would make moving objects more efficient in the vector versus list example, and that's correct, except I was staying with integers where there's no difference. The advantage of a vector will decrease when the objects get bigger, and therefore the overhead of the linked list will get smaller. But if that gets too big, then you will actually put a resource handle in there, a pointer, so that there will be back to 3 elements. But yes, moving will make that cheaper too. But I don't think that is that dramatically significant because of the way people use their data structures. Yes?
But a lot of the burden you put on the compilers, obviously compared to some of the interpreted code developing. When they specify like that resource, the developer resource versus a build, dependent build, and it's going to be perfect. How do you do that trade-off?
Build times are a problem in many cases. Part of the build time problem is the way people structure their code. There are a tendency of sort of including the world. Anything you could possibly need, throw in Windows.h and everything slows down. Or Unix.h. It doesn't, these are euphemisms, but if you take everything, it's being expensive. But even if you do it right, there are problems there, and there are very optimized builds in various places. Google hasn't released theirs, but they certainly have some optimized stuff. Clang has some specific optimizations to deal with this, and there's a lot of talk about various ways of improving the separation of the different concerns in the program, usually under the label of modules. But that will be future standards. All I can say, yeah, it's a problem. It's usually being handled, and people are putting in a fair amount of effort to make it better.
I've heard it said that people should throw away the first year's worth of C++ code that they write. And I believe you said that it takes about half a year to learn C++ or 2 years while being productive in the meantime. My experience has been that there's an enormous amount of non-obvious stuff that people have to learn before they can do pretty much anything at all in C++. To give an example, to put explicit before every constructor, which you don't want to use implicitly. How much better do you feel C++ Mark 11 might be?
Okay, I'll just repeat the question sort of. It takes a long time to learn C++, and maybe you should throw away the first years of work because it's going to be imperfect. Maybe how much better is C++ 11 for that? The first observation is you should probably throw away your first years of work in any language. The second observation is that because of the number of C++ programmers, the average C++ programmer is about average in the industry. New languages, especially experimental languages, tend to have above average programmers, and people who hang around with experimental language and PhD level programmers have a completely contorted idea of what can be done by a language. A lot of it is sociology. It's really hard to guess what people will do with the languages and language features. I mean, there are billions of lines of code out there, and they're not going to go away. And they're going to influence the way people write code. It has to fit into existing tool chains, existing library use and such. So there's an enormous amount of inertia here. If you're making a new project, you can probably do everything I recommended here, and if so, it'll be much easier than fighting your way through at a C or C with classes level of stuff. What I don't know is to which extent these ideas can be retrofitted into existing code, and what I don't know is how easy it will be to actually train programmers to do this, to teach the basic techniques. They're not complicated. You can write much cleaner code, but the real problem is the mass of existing code and existing programmers. To take a very little example of where things get easier, going back to move again, I write a move constructor, and now I can return a large vector or a large matrix. I don't have to fiddle with pointers and news and deletes and hack up some kind of local kind of garbage collector, or to plug in a general garbage collector. All of that just disappears. I mean, I think that will be able to be fitted into existing code without too much fuss. I think my code is getting dramatically simpler. Depends on what you're doing, of course, but some code gets half size. And it's not just the size of the code, but it's fundamentally simple.
What do you say to people who say that C++ is a dead or dying language?
It's a what? Yeah, people like to say that. I remember in about '96 when the Sun guys said that Java would kill C++, really dead in 2 years. Over the next 10 years, the C++ user population went up by a factor of 3. I also know that there was a policy in Microsoft that C# and the embedded language and the hosted languages were going to eliminate C++. They're putting more resources into C++. At the last standards meeting, there was 50% more people than there was in the previous one. We had the highest level of industrial participation in the last 10 years, and the user population has not gone down. It may have gone up. It's really hard to tell. There's somewhere between 3 and 4 million C++ programmers. How do you count that? I don't know. You can look at TOB, and you'll see C++ sort of steadily declining. But one, TOB measures noise, not use. It takes just one sort of undergraduate showing his prejudices to out-yell a couple of hundred professional programmers. And secondly, what it reflects is the difference in what programmers are doing. The script kiddies go up and up, but the people dealing with infrastructure and sort of serious professional programming are not actually going up that much. I see C++ slowly filling its natural niche and keeping steady to slight increase in absolute numbers. We're talking about millions here. I don't see any evidence of it going away. But people have liked to predict C++'s death from day one. There was AT&T managers that canceled the C++ project 3 times before it was shipped. In each case, they got a surprise. There was no C++ project, so they couldn't cancel it. And 2, they couldn't afford to get rid of it because they already depended on it. I think, I mean, you've used C++ many times today, indirectly, but it is there, and you can't see it because it tends to be deep underneath it. There's these cell phones that sort of comes up with a cup of coffee shining. What do you think they're implemented in? Java? No. Who did the Java virtual memory, for starters? Who did all the signal processing that goes underneath? It's not going away. It's not dead. It's actually very much alive and kicking and evolving into something hopefully better. I think I've ignored you a couple of times. Sorry.
So you advocate type-rich, type-safe programming. Excellent idea in my view. You picked an interesting example, though, with sort, Q-sort, because the signature is notoriously difficult to type. Sort takes arrays of items which must be comparable with themselves.
Yeah.
How precisely can C++ 11 statically type check that constraint?
In C++, you will write a template, and the strength and the weakness is that you get duck typing for templates. And so what you get is all the information is maintained throughout the compile time change, and you get basically perfect type checking and perfect inlining. However, you get the check too late. Just like where in duck typing you will get an exception at runtime, in C++ you get a compile time error possibly deep into some template code. And the error messages are horrid. I've been working on this problem for a while. We had a solution for C++ 11. Bit of realism came into it, and we just couldn't do it well enough. And so the work on concepts is carrying on. I have some designs that are radically simpler and should work, but it'll be at least another 5 years before we can get that into the language. But the way to think about templates and the techniques we use for solving that problem is it's duck typing. We get type safety, but we get it too late. So if you make a mistake, it's an ugly mistake. But if you don't make a mistake, you get all the benefits. When I designed templates, I had some choices to make, and I could get the checking up front. But if you don't want the checking up front, you can put in some virtual functions and get a perfectly checked interface up front, but you get indirect function calls. They're very hard to optimize away. So with perfect early checked interfaces, unless you do something really clever, you get inefficiencies. And I was in the business of trying to put arrays and sort of the Q-sort-like things out of business. And you don't do that by running slowly. The C++ community is quite obsessed with performance, and some people in irrelevant ways, but some people in relevant ways.
Okay, I think let me just say a few concluding words before you move on to the reception outside, where I hope you'll make some new friends. So, Bjarne, thank you very much for giving us such a fantastic start to the new Wheeler Distinguished Lecture Series. So I hope you will all agree that here is a man, he's a fella who has changed the world. His persistence has been amazing, from the intellectual concepts initially, through pushing back on AT&T managers, through standards over and over again, and indeed to having to suffer by traveling to Hawaii for the cause. So I hope you will join me in thanking him for a fantastic and brilliant lecture. Thank you very much.
And I'll be around in Cambridge for the next half year, so thank you.